Okay, so today is the first day in class, so let's just do a ritual thing. You know what it is. Yeah. I want you to create something like this. This is called avatar. Okay, it's nothing, just a piece of paper inside of protective film. So important thing, okay? Do not write on top of protective film. You need to remove the paper. I mean, I have to say this stupid thing over and over and over in other class because people just think straight. You have to take the paper out and then put your name really big, put your avatar. Okay, good. Simple. So let's do it. Let's just do that. Okay. It's just one of those things I have to do at the very beginning of each class chapter. If you don't write your avatar, nothing will change. No problem. And let me close the door because, again, projector's being so pathetic, you can see anything. All right. And Connor and Matthew, whenever you show up in class, I'm going to make you avatar, okay?
Dr. H, I already have my avatar from Arrow 1 still, so I think.
Oh, you're gonna recycle that?
Yes, sir.
Just to check. Yeah, that's fine. You can do that. No problem. I did this in, I think, Arrow 1 class. There's one student literally spent 30 minutes creating avatar. I had to wait and wait and wait. Okay. Anyway. So suppose if you want to make it like a completely perfect avatar, you can continue working, keep your marker, take it home, continue working on it. That's fine. So this is how I take attendance. Okay. Attendance is only required for tracking purposes, not for grading. Suppose if Jimmy's got positive, who was sitting right behind you, who was sitting next to you, that's what they want to know. So that's why I'm taking this attendance. I don't want to do it, but I have to do it because they forced me to do it. So this is the way I do take attendance. So at the very beginning of each class, you bring this avatar all the time to the classroom, and then you just hold up like this, right? Then I'll take the video. That's my attendance. It takes 1 second. That's what it is. Are you done? Still working on it? Oh, just don't worry, finish up. This is the first day. Let's take it easy. Especially this class is not that tense like Arrow 1. Go ahead.
So I never took Arrow 1 and I'm in fluid mechanics right now. Is that a bad move on my part? Or?
No, that's okay. I mean, Professor Ashworth, who created this class, didn't put Arrow 1 as a prerequisite for this class. He said, there's nobody taking this class if I do that.
I spent about like 15 hours this weekend looking over your Arrow classes stuff so I can do that quiz. So I struggled pretty hard on that one.
As long as you can survive, I don't mind. I mean, I do my best to answer your question. And then suppose this is a class which is heavily like a group project oriented kind of class. So you can literally hang on to your team member. Who's his team right now?
I'm in team 2.
Team 2. Who's team 2?
Nobody. Probably those 2 guys.
Those 2 guys, team 2? Are you guys team 2? Connor and Matthew?
Yep, that's correct.
Oh, okay. So he took my AR1 last semester, right? Is that right, Connor?
Yep, last semester, and I think I got a B, if I'm not mistaken.
Yeah. Okay. So anyways, so there are lots of information you can kind of teach and share each other within a group. That's not a problem. Okay. So let's just take a attendance. Okay. Yeah. Yeah.
Steve.
So this is attendance.
You should have wrote Steve. You should have wrote Steve on it.
And then actually, you know, in aero class, right in the middle of a class, okay, there's one person with heavily like protected with mask and everything, just open up the door and walk right in and asking question, is technology working? Then I said, who the hell are you? And he said, I'm IT. Then I said, okay. If something's wrong, I'm going to call you. Just get out of here. This is the real story. It actually happened. So it may happen today too. Just don't be surprised how hostile I sometimes I get. Anyways, because I'm not using any technology in this classroom. I'm just using projector screen. Everything else is all mine. Do you know this? Okay, that's how pathetic it is, the situation. I can never do anything if I rely on those people. Okay, this is mine. This is everything is mine. I'm using projector. That's it. And projector is as pathetic as you can see. All right. So joking aside, let's just get started. Because everything's recorded, I shouldn't be too radical or anything. Okay, so for those 2 people, I mean, I don't have I don't have even audio in this classroom today. I don't know what happened. So your sound is very weak. So if you want to say something, you literally have to yell at me, because the only sound you have right now is my laptop speaker. I may end up bringing my own speaker. I don't know. Anyways, okay. So don't hesitate. Even though you are online, I want you to feel at home right here in the classroom with the rest of your teammates. Jordan, here we go. Are you seeing Jordan? Okay, here we go. Okay, let's just get started.
Can we just get a better classroom?
Yes, but they didn't give us better classroom. Too bad.
Can you request another classroom?
If a strong request coming from student body, they may listen.
One of my classes.
Request from professor is usually completely ignored.
Like you can't hear anything, you can't see the board. It's absolutely insane. It's asinine.
And DLC.
Yeah.
What is it?
Class of the DLC.
DLC, right? Yeah, I know. I had lots of horror story from my own son. He's a freshman in biology. All sorts of horror stories. There's one professor actually doing Zoom session in the back seat of the car parked right outside the public library using Wi-Fi.
Oh my God.
Oh my God, that's right. I said, oh my God, is that teaching? And you guys don't complain about it? Yeah, it's a true story, okay? I'm not gonna name who's doing, but.
So if every single student complains, can we get a better classroom?
Well, I guess it's a stronger power than me complaining like hell. They don't care.
And you're the one paying for all this.
Yeah.
Huh?
So can we just all like write a petition?
Yeah. Okay. So let's move on. Let's just run something in airplane. So this class is all about airplane. So of course, aerodynamics is somewhat foundation of this class. So if you took aerodynamics, you kind of know like airspeed. You know, airplane, of course, need to determine airspeed. If you took aerodynamics, I actually went through the very origin of equation. Okay, so this is something called airspeed equation. Where does that come from? I think we covered that. Okay, and then that airspeed equation depends on your flight regime. In other words, if it's roll speed less than 0.3 Mach number versus more than 0.3, which is compressibility kicks in, how can we handle that? You know, density is no longer constant, but still I want to determine airspeed. What kind of principle we have to rather pick it up rather than just the roll speed equation. So those are some physics basis of physics which we cover in Aero. Now in this class we are going to actually apply to the practical sense that when you design and build airplane, how can you calibrate airspeed starting all the way from instrument? This is the instrument indication, and then you have to somehow calibrate to come up with a calibrated airspeed. And then after that, you are going to come up with equivalent airspeed. Equivalent airspeed is essentially if okay, your flight altitude is hypothetically right now sea level, what would be the airspeed indication? That's equivalent airspeed. And then, of course, you really want to know true airspeed. What is the true airspeed? And then true airspeed is not the same sometimes against ground airspeed. So those are the things we want to talk about, okay? Right, I think we stopped at the page 4. So today, let's just take a look at page 5. Airspeed indicators. This is a practical application of a pitot-static probe, which is a device combined with differential pressure measurement, differential pressure transducer type of device, which is on board on airplane. Combining those two devices actually determine airspeed as you in flight. Okay, what is the mechanism? And then, of course, any good pilot know that whatever your airplane tells you right now, right here, is a lie. It's not accurate. Any good pilot knows that. I'm not going to trust this number my airplane tells me. So the pilot should always go through the calibration process to determine what is the real airspeed, true airspeed. That's what I want. And then sometimes the ground control people says, what is the ground airspeed? That's what I want. It's not necessarily the same as true airspeed up in air. Ground airspeed could be different if you have a crosswind. Okay, so all sorts of things, step by step. Let's just take a look at it. Okay. So, of course, pitot-static tube combined with Bernoulli's equation, you can determine airspeed equation. Do you remember this? Do you remember this from fluid mechanics? I hope. So this is Bernoulli's equation, okay? Infinity is a free stream. 0 is a stagnation. Stagnation is a velocity 0. So pitot-static tube, right here at the stagnation point at the tip, you are going to sense P0. P0 is called total pressure. It's called total pressure point, okay? Right here, let's just zoom in a little bit more. Okay, and then on your side, those are the side port, sometimes called static port. Static port actually senses free stream static pressure, P infinity. Okay, so you can basically take a difference between them. So again, pressure differential needs to be somehow determined. Some kind of pressure differential sensor. Okay, and this P0 minus P infinity, this is the pressure difference between total pressure to the static pressure. What kind of pressure this thing is, by the way? Just sanity check. What kind of pressure is that?
Dynamic pressure.
Dynamic pressure. Here we go. Again, dynamic pressure, right? What is dynamic pressure? 1/2 rho B squared, right? So from there, you can determine B, okay? So that's where this equation comes from. Let me just write it down something. So Bernoulli's equation, once again, basically says the static pressure plus dynamic pressure is equal to total pressure. This is 1/2 rho d squared, right? So this Q infinity is essentially P0 minus P infinity. That's what I'm talking about. That's dynamic pressure, right? Dynamic pressure is 1/2 rho B squared. So what is B infinity, which is the square root multiplied by 2. P0 minus P infinity divided by rho. It's basically coming straight off of Bernoulli's equation. So anyways, this is called airspeed equation, okay? Now, airspeed indicator is essentially a real device, something called airspeed indicator. Now, airspeed indicator is manufactured in certain way, okay? So airspeed indicator basically without any calibration indicates whatever it senses. It's called airspeed indicator, indicated airspeed, BI, okay? So BI is essentially coming straight off of this equation. So P0 minus P infinity is a dynamic pressure which every aircraft has a capability to determine such a thing because of the pitot-static probe. Basically tells you only one information, pressure difference, okay? That pressure difference is a dynamic pressure which is sensed. And then without any calibration, airspeed indicator indicates, this is called indicated airspeed. Here we go. So this is the starting point, BI. Okay. So there are lots of issues here. One of the most difficult issue is, how about this rho kind of thing? Rho. So if airplane is flying in certain altitude, this thing is impossible to get. In other words, density, how can you measure density? Do you have a density sensor or something? No, you don't. Density is not measurable quantity because it's how much mass is packed up with a given volume. Are you going to collect this much volume of air as you fly and then count how many atoms and everything is in it? How much mass do you have in it? Of course, there's no way to determine such a thing. So density is at least non-measurable quantity as a direct sense. It's impossible. So what people do, in other words, they need to rely on the information they can get instead in airplane. What kind of information can you get in airplane? Of course, airplane can determine pressure as it flies. Static port gives you static pressure. Temperature is question mark, but yeah, oftentimes you can get temperature too. Accuracy is question. It's oftentimes called OAT, outside air temperature. Can we get this? Kind of. That's your answer. Okay, small airplane, maybe not. Big commercial airplane, possibly. OAT is always a question mark, but you need that information, OAT, together with the static pressure you keep sensing. Those two information are necessary to determine density. So that's why we have to go through the multiple process of calibration. So starting from indicated airspeed, okay, it basically says, okay, this indicated airspeed is not the speed at which the aircraft is moving through the air. So this is just the airplane thinks this is how fast you're flying, and no pilots trust it. I don't think so. So I really want to know the real airspeed. Okay, so first step is we are going to convert indicated to something called calibrated airspeed. That's C. Next step is calibrated to equivalent, that's E. And then equivalent to true, that's T. And oftentimes to ground. So this is the calibration process, something called ICE-T or ICE-TG. Okay, step-by-step process. You're going to convert one way of saying airspeed, indicated airspeed, to calibrated airspeed, to equivalent airspeed, to true airspeed, to ground airspeed. Okay? So before you do such a thing, let's just take a look at very simple exercise here. Example 812 or example 32. By the way, I'm kind of curious. Did you buy a textbook of this class? Textbook? Anybody? Anybody? Nobody? Nobody bought the textbook? Well, what textbook? Well, that's an interesting question. This textbook. This textbook. Heck no. Okay. So this is the textbook I'm using for this class, and then this author Grant and other authors, those are professors at the United States Air Force Academy. So those are all Air Force people. Professor Ashworth is part of it. This class is influenced very heavily by like a skewed one group of people. It's like Air Force people. Okay, so suppose if you are ROTC Air Force, man, buy it. Buy this book. I mean, this is gonna be your future. You're not gonna regret it. This is a nice book. The one problem of this book is the book contains tons of mistakes.
Yes.
Especially equation, derivation, calculation, punching numbers, tons of mistakes. You have to realize, wait a second, and the number comes up right. The number comes up right. Oh, wait a minute, you are missing, I mean, one digit off here. I mean, I realized those things as I create these notes. Tons of errors. So I had to correct it. So actually, my note is based on this textbook. I think the note is much more accurate than textbook, because the textbook originally contains lots of errors. I corrected everything. Anyways, so I would actually recommend this book if you are seriously interested in airplane and design, and especially if you are Air Force, already associated with Air Force. Those are the people controlling airplane design. Okay? So no regret. You can buy it, no problem. It's not expensive textbook anyways. I think $80 or something. It's from AIWA. Okay, $80. It's like your lunch money. If you are in California, it's a lunch money. I shouldn't say any political comments. Okay. So let's just take a look at it. Sorry about that. I need to look at my cheat sheet also.
Wow.
Yeah, this is instructor version of notes.
Can we get the instructor version of those?
Yes, you can, but you're probably not going to run anything because you don't have to do anything. Too bad. Okay. So example A12. Let's take a look. A manometer connected to a pitot-static tube, as shown in the figure 3.6, has a difference in the height of the two columns of water of 10 centimeter when the pitot-static tube is placed in a flow of air at the standard sea level conditions. So it's quite important. This textbook actually loosely used this kind of term, or air at the standard sea level conditions. I don't like this actually. So if you went through quiz 1, okay, I actually love to say something more specific. Okay, standard sea level pressure only, not the temperature. Standard sea level density only, not the temperature pressure. I want to say those kind of way. Do you understand, Jessica? I think she understands why. Too bad. Because lots of people say, if I write this kind of statement, oh, okay, every condition is standard sea level pressure, temperature, density, blah, blah, blah. No. Almost always no. So I want to say more specifically, pressure, yes, you can assume sea level, but not the temperature, not the density. Sometimes I try to always say that, but sometimes I may not say it, intentionally not say it. Now, in this problem statement saying that flow of air at the standard sea level condition, this really This really gives you an impression, hey, everything's standard suitable. Okay? In this case, yes, but oftentimes other cases may not. And may not means you should always ask question. Okay, well, I guess you probably don't know what I'm talking about. Okay, so let me just be more specific. Suppose if I say not the flow of air, but the pressure at the standard suitable, if I change the word, it's just one word. This really means that pressure is a standard suitable value. Yes, you can, because it's written here. But who actually said temperature and density is also standard suitable? Who actually said it? Who said it? Nobody said it. Nobody said it. That means if you assume it, it's a wrong assumption. Okay? So let's be careful. Does it make sense? Did you actually do quiz 1? Yeah. I hope so. Yeah, okay. Okay. Yeah, okay, good. Sometimes you have to learn hard way. Too bad. So be more specific. Yeah, I try to do that always. Let's be careful. So in this case, everything is a standard suitable, but not always. So how can we handle this kind of situation? Of course, do you want to go straight to airspeed equation, or do you want to apply Bernoulli's equation to get airspeed equation, then plug in the value? Either way is fine. I actually prefer starting from Bernoulli. Okay. So interestingly, I actually casually started with Bernoulli, but if you took my aero class, you probably don't do that, right? Before you apply Bernoulli, you go like, oh, wait a second. Are you sure about it? I mean, did you do quiz 1? Did you do quiz 1? You're not going to casually apply Bernoulli for just about anything, right? What is the condition of Bernoulli for this incompressible flow? In other words, Mach number should be less than 0.3. And I hope so, because there's no information for this, okay? The only information you can get is this is a manometer and the 10 centimeter difference. 10 centimeter, okay. So what kind of fluid is that?
Water.
Water. Is it say?
Yeah.
It says water, okay. All right. So Bernoulli's equation basically says that P0 is equal to P infinity plus rho times V infinity square over 2. So changing the form of this equation, you're going to have P0 minus P infinity. This is something called dynamic pressure, which is, of course, we know 1/2 rho V square. So this P0 minus P infinity is 1/2 rho V square, which is a dynamic pressure. This can be measured by this delta H measurement. Okay, manometer equation comes into play. What is the manometer equation you can apply for this situation?
Delta P is equal to rho G delta H.
Rho G delta H. Okay. So question is P0 minus P infinity. P0 minus P infinity. P0 minus P infinity. Yeah, okay, that's right. So this is going to be rho times G times delta H. Here we go. Okay. What kind of rho you're talking about? This is a water rho. Oh my goodness, you know, it's so getting so confusing. No, it's not. This is nothing new, right? What's this rho? Is this also water?
Air.
This is air. This is quite important because this is one of the very common mistakes in fluid mechanics, right? One of them is air, one of them is water. Don't mix up those two rows. Okay? So let's just plug in those values. Yeah. Okay? So P0 minus P infinity, which is essentially, this is called Q. Okay? This is going to be what's water density? Anybody know?
1,000 kilograms per cubic.
Well, how do you know? Because you're fresh out of fluid mechanics, and no one else is. I have no clue. Wait a minute. 1,000 kilogram per cubic meters. This is the number. You should actually memorize it because when you take professional engineer entrance exam, they're not going to give you this value. They assume you know. Okay, so memorize it. 1,000 kilogram per cubic meters. Okay, so that's the density of water. Gravity, let's assume this is a standard sea level, 9.8 meter per second square. Okay, delta H is given 10 centimeter. I don't like this. This is non-standard unit. I want a value with a standard unit. 0.1 meter. Okay. So 10 centimeter. 10 centimeter. How many centimeter for 1 meter?
100.
Okay, 100 centimeter for 1 meter. Okay, so let's just make it 0.1 meter. Okay. So if you calculate this, what do you get? Actually, you don't need a calculator for this, but you can go ahead, pick up your own calculator and pre-punch your number because I don't do it.
980.
980.
Yeah, you don't need a calculator. That's too bad, but 980. 980, what's the unit?
Pascal.
Kilogram.
Pascals, correct. Pascals is Newton per meter squared. Okay, so this is what we know. This is the dynamic pressure. Okay. Dynamic pressure can be determined by pitot-static probe combined with, in this case, U-tube manometer. Now, obviously, airplane is not going to use U-tube manometer and then measure this kind of thing. No, it is usually associated with digital transducer pressure difference or something like that. But this is the basic mechanism, okay? So now, based on this information of dynamic pressure, now you are going to plug in to the airspeed equation. V infinity is square root 2 times P0 minus P infinity divided by rho. And then, important thing is, what is rho? Do we know that?
No.
Not really. So let's say if this is standard sea level situation, you probably know the density of standard sea level standard value, which is something like 1.225, right? Kilogram cubic meter standard sea level density of air. If and only if you can determine this airspeed, please finish up airspeed. Somebody? If you are online, you can, of course, you can do that. Forty point
No, just 0.
40. That means 40. 40 meter per second. Pathetically low speed airplane. So this is an interesting exercise, but condition of this airspeed is hypothetically, you know the density right now. How many people actually know the density of this classroom? Nobody. Is there any way we can sense it? No. If you know the temperature and pressure in certain location, you can pick up your calculator and then you can estimate the density. That's the only thing you can do. Now, same thing happens in airplane. The airplane can only get certain things directly measured or sensed when you're in flight. Density is not one of those. Okay. So that's why we have to go through ICE-T or ICE-T ground conversion process. Next page. Okay. So let's just go through ICE-T or I can't pronounce, ICE-TG. This is a standard procedure step by step, okay? So first of all, indicated airspeed is a direct sense of indicated airspeed, and no one trusts it. It's usually not accurate. Indicated airspeed is instrumentation basically spits out. This is the indicated airspeed. So first step is I to C, right? So okay. So this indicated airspeed is something given, spits out from the airspeed measurement instrumentation. Then oftentimes errors are already associated with, of course, you need to minimize the error because that error comes from what type of pitot-static tube you're using. You can possibly use a horrendously bad pitot-static tube. Some crappy machinist made a pitot-static which has a tons of rough surfaces and the hole is not lined up and you have imperfection here and here. It's not the fault of airspeed indicators. It's the fault of a pitot-static. Okay, so that must be calibrated first. That's the step. Calibrated airspeed. Okay, usually this delta P comes in either positive or negative. It depends on what kind of pitot-static probe you're using. You may be using very, very nice and crafted very well pitot-static. This could be very close to zero. Okay, it depends. Okay, so this is the first step, calibrated airspeed. This is after the calibration of imperfections of your pitot-static probe itself. Or maybe, even though you started out pitot-static tube, a very nice condition at the very beginning, but if you go visit the flight line, people may bump right into the pitot tube and then make a scratch and maybe bend a little bit. Oh my goodness, let's fix it, kind of thing. It could happen. So those kind of errors need to be calibrated. It's called calibrated airspeed. The next step, okay. Once you determine calibrated airspeed, you are going to multiply the factor F to determine equivalent airspeed. Factor F, what the heck is that? It's essentially the difference in density between your flight altitude to the sea level. In other words, equivalent airspeed is what if your air density is sea level value. This is what your airspeed would be. That's called equivalent airspeed. Okay. So factor F is given here. This is something called factor F. Okay. So this is a quick chart for every airplane pilots have. They can basically. This is like a multiplication factor F, but it's in the table format. You don't have to even pick up the calculator and doing it. In other words, if your pressure altitude, which is calibrated airspeed, pressure altitude is your pressure measurement. So your airplane says, well, I'm flying 15,000 feet based on the pressure measured. So no one knows if it's really 15,000, right? 15,000 is estimated altitude. What you know is the pressure measured. Pressure measured happened to be a standard value of 15,000 feet altitude. So let's estimate we are probably flying 15,000 feet. That's called pressure altitude. Do you trust it? No, right? It's only estimate. Okay. Who knows today's a standard day? Okay, anyways. So pressure altitude 15,000, and then your calibrated airspeed is, let's say 200 knots. You're going to multiply 0.992 to have equivalent airspeed. That's what you do. Okay, so far. So what the heck is this equivalent airspeed anyways? What's the meaning of it? And oftentimes, well, you don't need such a thing because it is massively underestimated airspeed, right? Why do you need that? Mainly, you need it for your airplane design purposes. When you design your airplane, you need to present your airplane spec to your customer and then, hey, my airplane flies 2,000 knots. Okay, so which altitude you're talking about? So let's make it, okay, well, if the condition is standard sea level density, this is the airspeed of my airplane's capability. That's actually 150 knots. Well, that's not nice. Well, I thought you told me 2,000 knots. Well, if it's in outer space, if there's no drag or anything, gravity. So again, equivalent airspeed is airplane's capability to produce how much dynamic pressure, which is kind of important for designing purposes. Anyways, and the equivalent airspeed is always the lowest airspeed. That's why in this ICE process, E is lowercase, because this is the lowest value. Okay? So after you get equivalent airspeed, now final stage is, of course, you need some additional information. Additional information really is outside air temperature. If you are given outside air temperature, and then you constantly know usually your pressure, because airplanes just keep sensing pressure, and then somebody gives you outside air temperature, OAT, you can actually compute the real density of your flight altitude. Okay, if such an information is given, you're going to basically square root of density ratio multiplied to equivalent airspeed to have true airspeed. So this is the true airspeed of your airplane every pilot is willing to know. Okay? But this is actually required to know the real air density of your flight altitude, which is not at least directly measurable. Okay? Good. So there are a few notes here. Because the density ratio is usually less than 1, true airspeed is usually higher than equivalent airspeed, of course. Okay? And equivalent airspeed can alternatively be determined as the airspeed that would produce the same dynamic pressure at sea level as is measured for the given flight conditions. So am I saying something here? So that's why this is aircraft force generating capabilities. That's what the equivalent airspeed really means. So oftentimes this is important for your design purposes. How good your airplane can be judged by looking at the equivalent airspeed after you design and present to your customer. Okay. All right. Then at the very end, true airspeed needs to be converted to ground airspeed. Ground airspeed is obviously, you need to add the crosswind. Crosswind could be forward or backwards, okay? So relative to the ground, what is your airspeed? That's usually something which is quite important for like a air traffic control management type of sense. Okay, so that's the whole story. Let's just take a look at next page, okay? Do you have any question? Does it make sense? Did I cover those conversion in Aero 1? Sort of. It's not complete story though, because Aero 1 is more or less like a theory-oriented class. So I just wanted to kind of focus on how can I get this equation from what kind of physics and what kind of theory. That's Aero 1. Now this class is, of course, a lot more practical sense. How can airplane use such a thing? And what kind of steps the airplane pilot takes to calibrate airspeed. Okay. This classroom doesn't have it, but I think a classroom right next to it, they have a huge model of a flight computer, right? So, okay, now I'm trying this airspeed. Well, you can visit like a bookstore. They sell flight computer, and then you just usually don't care because you don't fly airplane. But airplane pilots, AS major guys, they go like, oh my goodness, this is it, kind of. Don't you have better one? I like OB type 01. You don't have it, and that's what I use. And yeah, you can. Next time when you visit bookstore, why don't you kind of approach those people and say, what are you looking for? Because I want to be a pilot, and could you just guide me through what's the best one? What's a flight computer anyways? Those are the good questions for you guys. Because they are going to act like, oh, you're a pilot wannabe, huh? Let me show you something. And then if you go to flight line, there's a vending machine. Vending machine actually sells flight computers. Because sometimes people just forget about it. Oh, here's a vending machine, you just buy another one. I'm not kidding, everything is true story. You have a vending machine of flight computers. Yes, and the flight log and everything. Those are required for your flight check, and sometimes people just sloppy enough to forget those things. They're gonna buy it in vending machine. Anyways, please make at least one very good friend of AS major, a pilot. Possibly ask them out for a weekend. What? Ask them out for dating or something. Pilots, you are engineers. They're very good because eye-opening, lots of things. Sometimes you laugh at it, sometimes you go like, oh my goodness, I didn't know that. Okay. Because engineer dating against engineers, it's not gonna work. It's always conflict. Okay, joking aside. Let's take a look at example 812. By the way, do you want to take like a short break in the middle, or do you want to continuously going?
Doesn't matter to me.
You don't have to take a break? Okay. Because now it's good timing to take a short break, like go into restroom or stretch and fresh air. Do you want to? Let's take like a 5-minute. Eh? Let's take a 5-minute break, and then as you come back, let's continue.
I think we just need to make sure that that's focused on the consistent. And it's not even ordering, it's just. Yeah. I don't think it hurts. Like you only see it because some cemeteries there.
We don't have to fortnight holiday.
Ah, there we go. Everyone will understand you went down. It doesn't matter. Yeah. I can make it better. I can make it. I can make my tail. I just had to click on it, and he just oh, okay. There's a whole you're right. I said it's hard for them. Yeah. No, think. Wait. Think. That's what they right? So no, you still have you think so far.
So you have to take the airplane for that.
So you report on the
So actually, it looks like we got 5 people still haven't signed up yet for team. And do you want one more team, like a smaller number of teammates? I can do that.
If you make up a team of 2 members, if that member all of a sudden drops this class, everything is on you. Is that what you want? I can do that, no problem. Because right now I think team structure is a 3-person period. That's it. Because we got 1, 2, 3, 4, 5 more people to sign up, and then how many slots open? It's like 5. So that actually making you kind of freeze up and think, and I can create one more team, allowing some of the 2-person member team.
That depends what the project's are.
Projects are fun project. Projects are fun project. You just design airplane and using software, completely virtual reality design. I mean, it's like a senior design without any of those presentation report process. Oh man, it's like an airplane design, only fun part.
Right? The manufacturer?
So senior design project without formal presentation, like a design review, all of those crap, I shouldn't say crap, all of those formal things. Professor shows up and say any sorts of bad things, and then you get frustrated, and then time pressed, schedule is on. I mean, airplane design can be done 100% virtual reality. And then you can play with it in any way you want to. You can actually try to fly it and without crashing it. And then you feel like, hey, this is the best airplane I've ever made. No one knows though, but in reality, I mean, you can only manufacture after that. I mean, right now, senior design process is something wrong. I mean, it's like an ancient idea. People nowadays don't do that. So, yeah. I used to teach actually senior design projects like a long time ago. When I was a new faculty here, like 20 years ago almost, I was forced to teach senior design, not knowing what it was. Dr. Matler, he was a chair, now he's a dean. He's the guy hired me, and he said, oh, Shigeru, you can teach airplane design. That's so prestigious. It's a lot of fun. You can do it. Now, I can send you to this, like what, short course at San Francisco or something. I spent 1 week in a hotel, every day, 8 hours of lecture of airplane design, offered by a professor of University of Kansas, happened to be the professor I knew. Professor I knew, I can't remember. Helped me someone. That old textbook, rainbow color textbook. Ruscombe, Jan Ruscombe. Oh my goodness. Professor Jan Ruscombe. Have you ever heard of Jan Ruscombe's design textbook? 10 books of rainbow colors. Everything is typewritten, so they can't fix it. Published in 1980s, still used today. Tons of accumulated data from all the airplanes. And then he doesn't explain everything. So when you size the tail, this is the value. Okay, why? Well, believe me, just take it. It's gonna work. That kind of style. Ruscombe's design, ancient style. Everything is based on experience. So if you know how to do, you can do it. Kind of design. It's a good and bad both. Okay, lots of airplanes designed in the past are amazingly great. How did you do that? I don't know. This guy did it. Yeah. So I taught the class, and then now I realize that's not the way we design airplane these days. We have to do a little bit better. That was more disseminated, and then based on the theory and the simulation and then the fact-based. In other words, if your simulation modeling is accurate, you can accurately sort of predict performance before you even build it. Otherwise, it's too risky and too expensive. Okay. So the software now is available. Software is, I think I introduced very first time in last semester. If you took my Aero last semester, I kind of started to seriously apply this software. Okay. And then this is the danger of this thing is this is open source software. So there's no guarantee. No one is going to help you. If it doesn't work, you have to figure it out. Okay, X-Flyer 5. This is open source software originally released only in Linux community. Okay, now it's available for Windows, so you can download for free. Pretty free. Go ahead, question.
Just a quick question.
Yeah.
The CFD, what program do you guys use here for the
CFD? CFD is, you're talking about solver?
Yeah, which one do you use in your lab?
Anything. I mean, if you want to bring your own solver, we can install it. That's the flexibility of our lab. Our standard is ANSYS, either Fluent or ANSYS. One more thing is Fluent or I can't remember because I don't use it. Yeah, ANSYS, two different types of, well, both installed, so anybody can use it if you know how to use it. Other solvers also available. In other words, NASA's Overflow, which is, again, open source. Are you in the right class?
Don't think so.
Okay. Yeah. And then, of course, you can design and build your own solver code. You can install. We used to have a Star CCM Plus, which is CD Adapco, which is a British company. Some of the school actually use that, but I decided not to because I don't want to run like two different software. One is enough if it's working. And then OpenFOAM, which is also a free software solver, in which we can install, of course. So anyways, X-Flyer 5 is not the CFD code, though. This is a design tool. In other words, airplane's performance can be predicted based on the panel method plus boundary layer theory, in which we covered it in aerodynamics. So it's a combination of Euler's-based solution plus boundary layer theory attached on top of it. Okay, plus some of the compressibility effects, Prandtl-Glauert correction is in it. So that's the software. So the software is 100% theory-based, but if you do a good job, you can fairly accurately predict airplanes' aerodynamics. Because airplanes' aerodynamics is a starting point to predict your performance of your airplane. So that's why first unit A and B, that's all about aerodynamics. And then unit C is airplane performance based on airplane aerodynamics. And unit D is stability and control analysis. Okay, that's what this class is. This software can do all, literally everything. Okay, so you can design your shape to begin with, cross-sectional shape. Okay, this is my choice of cross-section. How's that? You can even design it and name it. All right. There are a tremendous amount of cross-section of wing, and there's so many names. Some of the names are someone who actually created. Okay. Well, I make this name Hayashibara cross-section. You can do that. You can design your own cross-section to begin with. And then based off of it, you're going to analyze aerodynamic properties of cross-section, 2D aerodynamics. Based off of it, you can design the wing. Then the wing performance can be predicted. And also the wing and the fuselage is integrated. And also you're going to add on your stability surfaces, like a vertical, horizontal tail. If you want to make a biplane, is it working? Biplane, by the way.
I just have the wings in there.
Okay, so biplane and braces, and then tail, and then control surface, and then high lift devices, flap system, or wingtip shape. You can actually integrate motor, and then the weight of the motor size, and so you can do everything pretty much. This is the tool for airplane designers. And you can go all the way to the end of a stability analysis. Okay, so that means, here's what it means. If you master this software, you can design your airplane in any way you want to until you are fully satisfied. Okay, and then if you are convinced that, hey, this airplane is so cool, it's gonna fly, let me make it, and then find out if it's really true. Okay. So I don't know if I teach senior design once again, I will probably turn everything virtual reality. And then some people say cool, some people may explode. Maybe Air Force people, they say, oh, this is not the design. Senior capstone is supposed to be, integrated with like a formal presentation and a report process and blah, 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 blah. I don't think so, but some people still believe in it, right? So that's just a formality process, because nowadays I don't think even in industry do such a thing. They probably spend tons of time simulating, modeling, predicting, right? So that's the skill set you probably rather want to have, I think. This is a software actually developed by a professor at MIT, Professor Mark Dorello. Okay? Mark Dorello, yes. Everybody knows him, a god of aerodynamics. And then years ago, one of my students who graduated in my research lab applied to graduate school, and he actually applied to MIT, and then he got accepted to MIT, and then he went to Boston and then met this Professor Mark Dorello. And then he said, oh, I'm not going to work with him. He speaks in a certain way. It's almost like I'm king of universe, you are dumbass kind of attitude. I'm not going to work with him. He said it, and he went to France instead. But now he's got PhD and working at the Rolls-Royce. Now the Brexit happened. Too bad. Anyways, things happen. Okay. So let's just do something. I just keep talking. Well, actually, 5 more minutes to go, man. So I don't think I can do this. Wait a minute, I'm showing master notes to you. Too bad. Okay.
That's nice.
So let's just take a look at master notes. Okay. Too bad. And manometer connected to a pirostatic tube, as in the figure. Wait a minute, didn't I do that?
What?
It's like a déjà vu. Well, okay, anyways. There's a difference in the height of the 2 columns of water, 10 centimeters, blah, blah, blah. I think I've seen. Okay. What is the velocity of the airport? Didn't I do that? What's the point? Is this like a big typo? This is 3.2. This is 3.2. Wait a minute. Same example. Okay, so there are a few things I wanted to point out. Something's wrong here. Let me double check. This could be a massive typographic error. If so, I apologize. No. Wait, what am I thinking? I have no clue. I feel very weird because it doesn't make any sense to me, even though the person who created this note doesn't understand what it means. So, yeah.
Instead of miles per hour.
Then all of a sudden, I'm talking about knots. Nautical miles per hour. Yes, let's just finish up today with the nautical miles per hour information. Let me just review my own notes. Okay, sorry about that. I made up this notes last semester, so this is fairly new notes, so it may be a devastated mistake or something. I don't know. Let me just think about this. But the nautical miles per hour is more or less the standard measurement of airspeed. Okay. Okay. So we're going to use Kn or KTS. Either way is fine. So this is the airspeed. This is nautical miles NMI per hour. Okay, nautical mile is not the mile. Okay, it actually is 1 nautical mile is 1.1508 statute mile. This statute mile is a not common sense of 1 mile. Okay, nautical mile is okay. 5 more minutes. Okay, sorry about that. Nautical mile is based on the circumferential distance of the Earth. So here is the Earth. You are going to cut equal to 1 minute of latitude. Okay, so this is actually slightly more than the statute mile, which is random measurement. Okay, because airplanes flying, okay, above the surface of the Earth. So the nautical mile is going to be determined based on the circumferential distance of the Earth cutting into single minute of latitude. Okay, so we are going to actually quite often use knots in this class. So this is the beginning of knots. Okay, nautical miles per hour. Okay, let's be careful about that. This is something new from aerodynamics. So I still don't know what the heck, this solution doesn't match up with this problem. So let me just double check. I'm going to pick up from this page in the next class, okay, page 8. Sorry about that. Do you have any last minute question? And also another thing, let's just make up your team right here. I know 5 people hasn't signed up yet. So please spend some time, do some political campaign or something. Just to make up your team.
Political campaign?
Political campaign means, okay, well, Dr. H, I need another team because I know this team, I don't like those 2 people. I just want to avoid kind of. So if you have such a request, just let me know. Or if you want to join in, Jessica, right here, we can negotiate with her. But I think condition is you need to be SAE member or something, right? Okay, something like that. Okay, have a great day, and then see you guys Thursday.
Robert.
Do you have any questions, people online? Have a wonderful day.
You gotta get off of your game.
What was the freeware software you said?